So we're going to go through a few questions from the textbook chapter 3, starting with exercise 3.3, question 13. So this is about the pendulum. It's set swinging. The first oscillation is through an angle of 30 degrees. So we can say that A, the first term, is 30 degrees, and each succeeding oscillation is through 95% of the angle of the previous one. So that means that the R value, and this is a geometric series because it's multiplicative, you're 95% of the previous value, there's a multiplier of 0.95. So after how many swings is the angle through which it swings less than 1 degree? So the first swing is an angle of 30 degrees, R is 0.95, and we are looking for the nth term, UN, to be less than 1 degree. So remember the formula for the nth term, AR to the n minus 1. We want that to be less than 1. So 30 multiplied by 0.95 to the power of n minus 1, less than 1. Divide by 30, 0.95 to the n minus 1 is less than 1/30th. And let's then take either natural log or log base 10. I'm going to take log base 10. So I'll write down log of 0.95 to the n minus 1 less than log of 1/30, like that. Then remember your log rules. This can come out to the front. So n minus 1 log 0.95 is less than log 1/30th. So again, we're going to divide by the 0.95. And remember, log of 0.95 will give you a negative value. You can just see that over the side here. I'll write it out. Log of 0.95 is actually equal to negative 0.022. So it's less than 0. It's a negative value. So when you divide by log of 0.95, we need to reverse the inequality sign. So we'll be left with n minus 1 on the left, and that is greater than, reversing the inequality sign, log of 1/30th over log of 0.95. So this then gives us n must be greater than this calculation here plus 1. So that means n is greater than 67.308, which means that we would need to give n equals 68. Now I'm aware that the answer in the back of the book here is 67 rather than 68, but that's wrong. It's got to be 68, otherwise this isn't going to work. So there is a mistake in the back of the book here. The correct answer is 68. Also, it's worth pointing out that the wording in the back of the book actually says after 67 swings. So really, by implication, they're not saying the answer is 67. They're saying after 67 swings. So really, that means 68 swings. So for part 2, the total angle it has swung through. So when it says total, that tells us we are looking at the sum of n terms. So we need this formula here. So that is 30 multiplied by 1 minus 0.95 to the power of 10. So we're looking at the sum of 10 terms, the total angle, after 10 oscillations, over 1 minus 0.95. Input that into your calculator, and we get 240.757 ... So 240.8 degrees to 1 decimal place is the total angle. Now, what is the total angle it swings through before it stops? Now, this is a subtle way of saying find the sum to infinity. By saying before it stops, we're basically implying that the oscillations will just carry on gently from side to side. And if you've ever seen a swinging pendulum, it takes a long time before it's actually completely stationary. And even if you think it's stopped, it's actually just oscillating from side to side with tinier and tinier angles, which means we're looking for the sum to infinity, which is a over 1 minus r. So that is 30 over 1 minus 0.95. Let's work out what that comes to, and it's a value of 600. So question 13 from exercise 3.2, quite a tricky question. we are told that the sum of the first n terms of a sequence is Sn, where Sn equals 2n squared minus n. So part 1 proved that the sequence is arithmetic, stating the first term and the common difference. So what I want you to imagine is that if we took u1, u2, u3, all the terms, un minus 1 plus un up to the nth term, and added them together, we would get Sn, the sum of n terms. Now, instead, imagine if we stopped at this term here, un minus 1. What would we have? We would have Sn minus 1, the sum of n minus 1 terms. So, if we were to subtract these two equations, can you see that you would get full cancellation of everything apart from, we'd be left with un, the nth term. And on the right-hand side, Sn minus 1. So the difference between the sum of n terms and the sum of n minus 1 terms is, of course, the nth term. So how does this help us here? Well, we know that Sn is equal to 2n squared minus n. Now, to find the sum of n minus 1 terms, we simply replace n with n minus 1. So that would give us 2n minus 1 squared minus n minus 1. If I were asking you to work out the sum of the 20th term, the first 20 terms, then I would ask you to replace n by 20. I want you to find an algebraic statement for the sum of n minus 1 terms, so replace n by n minus 1. So, expanding our brackets here to simplify this, n squared minus 2n plus 1 minus n plus 1 here. Keep simplifying. 2n squared minus 4n plus 2 minus n plus 1. I'm probably doing more steps than you really need to here to simplify this. It's not that difficult. And we get that. That's the sum of n minus 1 terms. So going back to this result over here, we can say that un, the nth term, is Sn, which is 2n squared minus n, formula that we were given back at the start, subtract Sn minus 1, which is this result here. So 2n squared minus 5n plus 3. And this will give us a formula for the nth term. So what happens? Well, 2n squared minus 2n squared is 0. We've then got minus n minus 5n. So we end up with 4n minus 3. Now, what's interesting about this is it's the format of an arithmetic sequence. It's clearly got a linear format to it. Now, if you want to, you can work out some terms. So u1 would equal 4 times 1 take away 3, which is 1. u2, 4 times 2, 8 take away 3, 5. u3, 4 times 3, 12 take away 3, 9. And you can see it's clearly an arithmetic sequence which has got a first term of 1. And you can see that the common difference is equal to 4. Now you can also, if you want to, write it out in the format of the nth term of an arithmetic sequence. If you remember, the nth term will always have the format a plus n minus 1 multiplied by d. So we could rewrite this formula as 1 plus n minus 1 multiplied by 4. And just expanding and simplifying this gets you straight back to this. So you can see it's the correct result. So by finding the nth term and showing it's the nth term of an arithmetic sequence, we've proven the result. So part 2, find the sum of the terms from the 3rd to the 12th inclusive. So that means we are looking for the sum of the terms between n equals 3 and n equals 12. So if you think about S12, that's u1 plus u2 plus u3 plus u4 plus all the way up to u12. Now, I only want the sum of the terms from the third term up to the 12th term. So if I write down what S2 is, it's U1 plus U2. So can you see that if you subtract these, you will get a nice cancellation, U1 and U2, U1 and U2 disappear, and then you're left with everything you want, the sum from the third term up to the 12th term. So we need to work out S12 and then subtract from that S2. Now we are given that Sn is 2n squared minus n. So let's work this out. This is 2 multiplied by 12 squared minus 12. Subtract 2 multiplied by 2 squared minus 2. And let's simplify this using a calculator, which gives us an answer of 270. So question 14 from exercise 3.2. This is a great question. Lots to think about here. So part 1. I'm going to write down the original formula we're given. Sn equals a half n, 2a plus n minus 1d. And we need to rewrite it in the formula Pn squared plus Qn, where P and Q are constants, and you've got to state the values of P and Q in terms of A and D. So this is just asking us to expand and simplify everything. I'll start off with the contents of this square bracket here. 2a plus nd minus d. And then let's expand again. So that's going to give me an plus a half dn squared minus a half dn. And then if I keep this term here on its own, so a half dn squared, but I take the other terms and I factorise out an n from them, I have plus a minus a half d bracket n. Now this is of the format Pn squared plus Qn. Can you see what P is? It's the coefficient of n squared, it's that. So P is equal to a half d. Now, can you see what Q is? It's the coefficient of n, so it's this. So Q is equal to a minus a half d. Now, part 2 asks us to explain why the nth term is given by Sn minus 1. So again, I refer to the fact that Sn is equal to U1 plus all the terms leading up to and including the nth term. Sn minus 1 means we add together all the terms up to and including the n minus 1th term, or un minus 1. Now, if we subtract these, then what do we have? On the left-hand side, we have Sn minus 1, and on the right-hand side, everything cancels apart from un, which of course is the nth term. So there's the explanation required, and we need to find a formula for the nth term in terms of P and Q. So in the last part of the question, part 1, we found out that Sn was equal to Pn squared plus Qn, and P was equal to 1/2 of d, and Q was equal to a minus a half of d. So what do we have to do? We have to find a formula for the nth term. So un is equal to Sn minus 1. So that's Pn squared plus Qn. Take away. Now what is Sn minus 1? So we want to replace n by n minus 1. So we've got P bracket n minus 1 squared plus Q bracket n minus 1. So that's what we're subtracting here. So I've got Pn squared plus Qn, subtract this result here, which is Pn minus 1 squared plus Qn minus 1. And now let's do some serious expansion, simplification, and collecting of like terms. So this will give me Pn squared minus 2Pn plus P plus Qn minus Q. Now, pn squared cancels with a pn squared. There's a qn here, which cancels with a qn here. So what am I left with? I'm left with 2pn minus p plus q, checking my signs carefully. So that's the nth term in terms of p and q. So the last part of this requires us to show that the sequence is arithmetic and find the first term and common difference in terms of p plus q. So let's look at the nth term, un equals 2pn minus p plus q. There are different ways of going about this proof. So I want to rewrite this as something plus n minus 1 multiplied by something else. So we want to write it in that form there. So 2pn minus p plus q. Well, if we put in n minus 1, we need to make sure that we have a multiplicative factor here that will give us a 2p. So really I want it to be 2p brackets n minus 1. Now if I expand this, I get 2pn, which I want, minus 2p, but I only want there to be minus p. So that means I want to add on a p here to make this work, and of course I need to add on a q here as well. So I can rewrite this as p plus q plus 2p brackets n minus 1. So here I would fill in p plus q plus this multiplied by 2p. So just for clarity I'll rewrite this here, p plus q plus n minus 1 multiplied by 2p. Now this is the format of the nth term of an arithmetic progression. Because it's got the form a plus n minus 1 multiplied by d. So what's a? P plus q. And what is d? Common difference, that is 2p.